Hello guys, my name is AbbasSamandov. Today I will be teaching you how to solve optimization problems and how you should be approaching them step by step. Right? This applies to in terms of concepts and how you should be approaching the problems to all optimization problems, but with the specific example that we're going to be using, the equations are obviously going to be different, right? But the principles I teach you are the exact same. So optimization is a method that you would use to find maximums and minimums of functions in real life situations. And usually you will be given some sort of a constraint. Actually, you will always be given some sort of a constraint. And I'm just going to give you an example here so you kind of know what I'm talking about. Let's say you have 100 feet of fencing, right? The problem would ask you something like, hey, what's the maximum area of a rectangular enclosure that we could make with this fencing, right? And I'm going to teach you how you would be able to find something like that with a different example here, right? So we're going to I'm going to walk you through this problem right here, right? So let's read the problem real quick, find out what it's asking us. Engineers are designing a box-shaped aquarium with a square bottom and an open top. The aquarium must hold 256 feet cubed of water. What dimensions should they use to create an acceptable aquarium with the least amount of glass? Now, a thing that I should note right away is that they're giving me the necessary volume. This is the constraint of the problem. This is what the volume absolutely has to be, right? And I'm looking for the dimensions of the set box. So I'm going to be looking for the sides, right? And another thing I'm going to know right away is that it's a square bottom. So the base of the tank is a square, meaning that the side's going to be equal. So the first thing you should do whenever you're starting to solve a problem like this is to draw a diagram like this. Boom. So we're just going to draw a tank right here, right? Draw a tank like so. It looks a little bit out of proportion. That doesn't really matter too much. I could fix it if I really needed to. If that bothers me, that's okay. Just keep it organized and a little bit neat to just not get confused in it. That's the main issue that could happen sometimes. I don't want to label it. I know that the sides are going to be equal on the bottom, on the base right here, right? So I'm going to label that as the same variable, and I'm going to label the height as y. And then I'm actually going to just quickly shade this in right here, right? Because I know that's open. I'm going to just indicate it on the diagram like so that immediately pops up in my head. Then I'm going to, the next thing you need to do is name and list all of your givens. So I'm going to do just that, and you should name them as well. So I know the volume, I'm going to call it V, and I know that it has to be equal to 256 feet cubed. Okay? Also, I know that I don't know X and I don't know Y, but I know that I have to find them. It's what the problem is asking for. So I'm going to state that, right? And I know that this is side, this is height, right? So whenever you're writing down your volume equation, you can actually jump straight to that, right? Volume. What's the volume of a equals V? You don't have to write it down again. I just did that automatically. So we know that volume is equal to side times height, right? So we're going to do just that, right? And you should write down your equation first, like volume equals LWH, right? Side height. But then I know that L is equal to W, and that's equal to X, right? And I know that H is equal to Y. That's what I set them equal to. So to be clear, label that just like so. And so your volume is actually equal to X squared Y, right? I'm not done with this. I know that it has to be 256, so I'm going to put that in the equation, plug that in, boom. This is actually going to be my secondary equation right there, right? Which is the next step. I'm going to tell you right now, you have to have a primary and a secondary equation with these problems, right? Sometimes one of them will jump out at you immediately, faster than the other, right? With this one, I was like, I just see it has to be 256 feet cubed. I'm just like, oh, volume. It jumps right at me. And I know that this is going to be one of my equations. But it's not the primary one. It's the secondary equation. You have to realize that whenever you're doing this, right? So what is our primary equation then, right? We're actually going to use surface area because we're going to be looking for sides, right? And another equation that will, other than the volume, that will incorporate the entirety of the tank, and we use the sides as a surface area. So I'm just going to quickly label it as so. This is surface area, right? And I know that this equals, now let me just go through this real quick. The surface area of a box like this is all of the areas of the surface is added up, right? But we don't have the surface right here, so we only have one base right here, right? So that's X squared. We're gonna put that in, and then we're gonna add these four sides, and all of their areas are equal to XY. So we can just say 4XY, boom. Now, this right there is the reason why we have a secondary equation. We don't want our primary equation in terms of two variables. We want it in terms of one. So we're actually going to isolate y in our secondary equation, like so. It's going to be 256 over x squared. And then we're just going to plug that in. X squared plus 4x, 256 over x squared. Now, the x and the x squared will actually reduce. So what you'll end up is, over here is a fraction 256 over x. And so whenever we multiply that through, it comes out as 56 times 4. That's 1024. This is my 1 over x, right? So we're trying to find the minimum surface area here, right? That's what we're optimizing, is the surface area. We're trying to find the minimum dimensions, correct? So minimum surface area, minimum dimensions. So what we're going to do to find that is take the derivative of the surface area, like so. So then 2x. Now, I would rewrite this, right? I'm actually going to rewrite this real quick, because whenever you're taking the derivative, even though this is an easy fraction and you really don't like dealing with the quotient rule, it's not something that, you know, is easy to do in your head. It's not intuitive. So I'm going to rewrite this as 1024x to the negative 1. Now that's a lot easier to deal with because you can just use the general derivative rule and you're good to go, right? So x squared is going to equal 2x in our derivative. Now minus, because the negative 1 will actually come down, right? So minus 1024 x to the negative 1 minus 1. So that's negative 2 right there. Is equal to 2x minus 1024 x to the negative 2. Boom. Okay. Next thing. You gotta set this bad boy equal to 0. So 2x minus 10 to 24 x to the negative 2. Bam. Go. Now, we're going to solve for x. That's going to be our critical point. That's going to be our min. And we're going to prove that it is a min in the end. So, 2x is equal to 10, 24 x to the negative 2. Sorry about that, we experienced technical difficulty. So, we left off right here. Here's what you got to do, right? Gotta get it back into fractional form. And then you multiply both sides by x squared, which is then going to equal 2x cubed, which is then going to be 2x cubed equals 10, 24 over 2, right? It's not going to equal 10, 24 over 2. It's going to equal 10, 24. Then you have to divide both sides by 2 to get rid of the 2 on this side. So then it's going to be x cubed equals 512 after you do that. But then what you want to do is you want to take the cube root of both sides, and then you end up with x equals 8. Now this is your min, but you have to prove that. So what you do with that is you do the first derivative test. We're going to draw a number line here, like this, right? This is 8. You can use any value less than 8. I'm going to use 1, right? Just use 1, okay? It doesn't matter. So what you want to do after that is plug it in to the derivative equation, right? This one is going to be the same thing. We're going to plug it in the derivative, right? And so whenever you plug it in to the derivative, whenever you plug in 1, it comes out to be less. It comes out to be negative here, right? Right there. It comes out to be negative. We're going to show that on the number line. And whenever you plug in, let's say we plug in 10. Right? Let's say we plug in 10. Whenever we plug in 10, it comes out to be positive. And I'll show you on the number line right there. So by first derivative test, since it changes from negative, the derivative changes from negative to positive at this critical point, right? This critical point is a min. So by first derivative test, 8x equals 8 is a min. Done. You proved that it's a min. Now, this is one of our sides. We're going to box it. But this is not the only one we're looking for. We're also looking for y. So how are we going to find it? The easiest way to do it is going to plug it into the volume equation we have right there. So y is going to equal 256 over 8 squared, which is going to equal to 256. I was trying to think of the best way to write it down to make it clear. 64. And that's going to come out to be 4 right there. That's our second side. And we're done with the problem. That's what it was asking us for. We got one side, we got the height. That's all it was asking for, is the dimensions. And that's it. So you got to do.